All right, so let's do some examples of finding domains of given functions. What I'm going to do is I'm going to use Desmos to draw the graphs of some of these functions, and then we're going to look at what we can see from the functions themselves. So let's come over here, and the first function we're going to look at is the rule is f of x equals 1 plus x squared. So this function rule, whatever value we put in from the domain for x, goes through this filter. Now there's a couple things to see here. The domain itself, well, I have no division by zero possibilities here because there's no divisions, and I have no square roots. So I'm going to be able to take any negative number and any positive number, including 0. There's nothing that restricts what I can put into this function. Now, if I inspect this, this has an even power. And anything to an even power will always be positive. So whatever I put into x, this term here will be positive. Right? If I put in a negative 5, this becomes a positive 25. So this will always generate positive numbers, except if I put 0 in, and then I get 0 back out. So my range, well, if I put 0 in, the plus 1 means that I'm going to be able to get a 1 back out and go all the way to infinity. If I draw this freehand and use the rules we have for drawing a function, this is the function x squared plus 1. So it's shifted up. Well, I can draw x squared shifted up. And I can notice that my range would be my y values, and I start at 1, and the only values I'm going to see are positive towards infinity. Well, let's look at that in a graphing utility. So let's see if I can get, that's not what I want here. Come over here. And I'll say that f of x is equal to 1 plus x squared. And why am I not getting a graph? Let's reload this. There we go. F of x equals 1 plus x squared. And I can visually see that I am starting at 1 on my range, and there are no values below 1. So visually, we can see the range that comes out of this. And if I go back to the rules, we can see in the rule set that I have no restrictions, so I can get any domain, but when I process this, I have this limited range. So this is what it means when we find the domain and range of a function. Let's look at another one. I'm going to have the function f of x equals 1 minus the square root of x. Well, now I do have a root. And you're going to see I will have a tendency to write roots in fractional notation. When we start processing, doing a little more calculus, this will help us with some of the power rules. So just to be noted, a square root is equal to the 1/2 power. A cube root is equal to the 1/3 power. A fourth root is equal to the 1/4 power. And we can see this because if I take the square root of something and I square it, my rules of exponents say I add the exponents or I get the x back. So you'll see I'll go to this notation periodically because there's some other rules we have where the power rule is easier to visualize. But with these fractional roots, if the denominator is even fractional roots, can't be less than 0. X cannot be less than 0, because that'll give imaginary numbers. So my domain is limited. I can start with 0, and I can go up to positive infinity, but I can't do anything else. And there's a couple things I can do here. If I remember my graph for the square root of x, that's the square root of x. This is telling me I'm taking the negative of that, so I'm going to come down like this. So that's negative x. And then in the 1 says I shifted up 1. So my actual function is going to look like this. And if I look at the y values I can possibly have, well, this will go all the way down to negative infinity. So my range will come up from negative infinity, and it'll peak and stay at 1. And that should be the range I have for the function. Let's do the same thing. Let's graph this in Desmos and look at a visual representation of it. So I'll do 1 minus square root of x. And here I have the highest value in the range is 1, and it scrolls on off down to negative infinity. So again, we compare what we see in the graph to how we process the rules, and we have the ability to check the domain and range of the function. Let's look at a division by 0 possibility that can come out. So let's look at a function here. And for nomenclature's sake, I'm going to make this a function of the variable t. So I have some g of t is equal to 2 over 2 squared minus 16. I want to put in all real numbers, but I can't divide by 0. So I have to know when t squared minus 16 cannot be equal to 0. And if I solve this, if I take the square root of both sides, I get plus or minus 4. Alright, when we take a square root in solving things, we get the plus and minus, and so this cannot be plus or minus 4. So I get all other real numbers. So my domain goes from negative infinity to negative 4. Then it goes from negative 4 to positive 4. Then from positive 4 to infinity. And so we have a domain that has 3 distinct sections in it. It has the section from negative infinity to negative 4, has the section from negative 4 to 4, and then it has this section from 4 to infinity. All in all, we say that t cannot be plus or minus 4. Here is the union of all other numbers that come from it. Graphically, this divides it into areas where it can exist. And this is positive for the negative 4, so I'm going to get 2 over some negative number, so I think it's going to look like this. And then in here it's going to be positive, let's see, 1, and I think we're going to have something that looks like this. So this is me looking at what the function does. I could plot some test points in each area. Let's say if I put 5 in here, 5 squared is 25. Oh, I have it upside down, right? Let's see, let's do some test points to make our plot look okay. So we know we have these areas in here, so let's test it when t equals negative 5. Well, negative 5 squared is 25. 25 minus 16 is, 25 minus 16 is 9, so that's 2/9. So it is actually positive here and positive here. Right, when t equals 5, I'm going to get the same value. So there's a symmetry between those two parts. And now let's look in the middle. If t is 2, then we get negative numbers. So I think we have something like this down in the middle. If we look at some test points. All right, t equals 2, I get 4 minus 16. That's negative 4 minus 16 is negative 12, so negative 1/6. So we have something like this on the graph. And we see those 3 distinct sections in the domain. Well, let's look at Desmos to confirm my algebraic curve sketching. So we'll come over here. We'll say g of t is equal to 2. Let me make sure my Desmos is showing for you guys. And g of t is equal to 2 divided by t squared minus 16. And we get a graph similar to what we sketched. So we have found our domain. And now if we look at our range, here's something really unique about the range. This gives me positive values, and this gives me positive values, where this section gives me negative values. But something happens here that these values really can't get to 0. And so if we look at the range coming out of this, we'll go back to this one. We definitely get a side where we go from 0, not including 0, to infinity on these positive parts. But what happens on the negative? We're coming in from negative infinity, and we get to a value that peaks at 0, right? Because 0 is where this is symmetric. Remember, t squared is going to give the same value on either side. Right? Negative 2 and positive 2 give the same thing coming out of t squared. So that all changes at 0. So the tallest point this gets to in the negative side is when t equals 0. And so when t equals 0, I get 2 over negative 16, or negative 1/8. And so there's this gap between negative 1/8 and 0, where there are no numbers within the range. We're going to learn that the points like this are called local maxima or local minima, local extrema, and we'll find the calculus of finding them a little bit easier than the algebra. But we kind of have to look at the patterns that we get from our functions to find some of the ranges. And pattern recognition is one of the goals of the mathematics we are doing.